Hi everyone, welcome to part 3 of our series on understanding series convergence. This time we're going to focus on comparison tests. So comparison tests are used when we have series that we can't immediately tell based on like an integral test or a p-series test or a geometric series test. We can't use those tests, but we can compare them to similar series that have that geometric p-series or integral characteristic. And actually, I should clarify, for some of these series, we could use the integral test, but it's much faster to use a comparison test, and you'll see that in some of the examples we do. So, if we go ahead and use a comparison, then we can pretty much tell if this series will converge or diverge, just based on comparing it to another series. So that's how it works. We have two comparison tests here, the direct comparison and the limit comparison. So let's go ahead and get started with the direct comparison. So let's say we had two sequences, a sub n and b sub n, right? So let's say that a sub n is less than b sub n for all values of n. So a sub 1 is less than b sub 1, a sub 2 less than b sub 2, so on and so forth. So if this is the case, then the sum of a sub n, or the infinite series of a sub n, must be less than the sum for b sub n, the infinite series. And this is pretty intuitive. If you just sum up smaller terms, it's going to be smaller than the sum of like comparative terms, comparatively larger terms. So, okay, so let's go ahead and examine this here. So, if this series for b sub n, if this converges, if we know that this converges, then the series for a sub n will also converge if, again, a sub n is less than b sub n. Consequently, and I'm going to put a note here, a sub n less than b sub n, consequently we can put it the other way around. So if b sub n diverges, then the series of a sub n will also diverge, but this is if a sub n is greater than b sub n. And this seems pretty intuitive, right? If b sub n, the comparatively larger terms, if they converge to a value, and then you take a sub n, which has smaller terms, they must also converge to a value. But they won't converge to the same value, but they will both converge. And consequently, if you have larger terms, b sub n, or if you have comparatively smaller terms, b sub n, and the summation of that diverges, then if you have comparatively larger terms and you add those up, then they will also have to diverge. That just makes sense. So let's go ahead and get started here. We're going to start looking at these three examples, and I will clarify there is an example that doesn't necessarily give us a result, and you'll see that. So let's start with the series from 1 to infinity of 1 over 9 plus n squared. So what we can do is let's pick the series 1 over n squared, and we know that this converges by the p-series test. Since 2 is obviously greater than 1, that means that it converges. So, what is the relationship between 9 plus n squared and n squared? Well, the denominator for this series right here is greater than the denominator here. So, if the denominator here is greater, the overall value is going to be smaller. Therefore, this series right here is smaller than this series. And since we have this series being less than a convergent series, this series from 1 to infinity of 1 over 9 plus n squared also converges. And this is by the direct comparison test. And I just like to abbreviate it with DCT. I don't like to write out direct comparison test. That's too many letters. So let's go ahead and move on to the next one. We have the series from 1 to infinity of 4 to the n divided by 3 to the n minus 1. So let's go ahead and compare this series of 4 to the n over 3 to the n. Well, this is actually the same thing as the series from 1 to infinity of 4/3 to the n, and this is just by exponent properties. And as you can see here, this is a geometric series, but since 4/3 is greater than 1, this diverges, and the reason is geometric. So, now let's go ahead and draw a comparison between these two. So you notice that this denominator is being subtracted by 1. Therefore, the denominator here is smaller than the denominator here. Therefore, A smaller denominator makes the overall value larger. So we put a greater than here. So since this series right here is greater than a known divergent, this series from 1 to infinity of 4 to the n over 3 to the n minus 1 also diverges by the direct comparison test. Now let's go ahead and move on to our last example here for the direct comparison. This is n over n squared plus 1. So let's go ahead and actually try to compare this with the series of n over n squared. But what's n over n squared? That's 1 over n. So we're going to compare it with the series of 1 over n, and we know that diverges because 1 over n is it doesn't pass the p-series convergence, and it's also the harmonic series, and the harmonic series is a known divergent. So what is the comparison between this? Well, if you notice here, the denominator is being added by 1. Larger denominator, smaller overall value. Therefore, this right here is going to be less than this. But we need to pause for a second here, because take a look. We have this series being less than a divergent series. Is this series going to diverge? Well, yes. I mean, we did this with the integral test. We figured out that it diverged, but we can't exactly say that this series diverges by the direct comparison test, because if we compare this with, if we had 1 over n squared here, and we know that's going to be less than 1 over n, and 1 over n diverges, we cannot say that 1 over n squared diverges by the direct comparison test, because 1 over n squared converges by p-series. So, therefore, we say that this test result is inconclusive. And whenever we have an inconclusive test result, we put a sad face. That is a terrible looking sad face, Jesus. There we go, that's a better looking sad face. Thankfully, there's a fix for this. We can actually get a result through a comparison, and that's by something called the limit comparison test. So, the limit comparison test states that, let's say we had two sequences here. Let's say we had a sub n and b sub n, and both of these sequences have non-negative terms. So, let's define this value c right here as the limit as n approaches infinity of a sub n over b sub n. Now here's the rule here. If c is both positive and finite, in other words, if c is between 0 and positive infinity, then the series for a sub n and the series for b sub n will both converge or both diverge. And we can say that this is true because if we are taking the limit as n goes to infinity of a sub n over b sub n, the ratio of sequences, and we get a positive value, if b sub n converges, then a sub n pretty much acts like a scalar multiple of b sub n based on this ratio. So therefore, if you're multiplying a convergent value by a scalar multiple, you're just going to get a convergent value again. So that's how that works. And the same can kind of be said for divergent, right? Because if you have a scalar multiple of a divergent series, then you'll have another divergent. 3 times infinity is just infinity. But again, if you had 0 here and you had a known divergent series, then you're going to get 0 times infinity for another series. And 0 times infinity, we know that as indeterminate. So we cannot say that the limit comparison test gave us a conclusive value. All right. Moving on from that long explanation, let's go ahead and get into some examples here. So, we have the series from 1 to infinity of, again, n over n squared plus 1. And just like last time, we're going to use the series from 1 to infinity of 1 over n, and we know that diverged by, again, it being the harmonic series. So, okay, I don't know why that's erased there. So, what we're going to do here is we're going to take the limit as n goes to infinity of this divided by this. So we're going to have the limit as n goes to infinity of n over n squared plus 1 divided by 1 over n. And multiplying by the reciprocal, this just gives us the limit as n goes to infinity of n times n, or n squared, divided by n squared plus 1. And now n squared plus 1, n squared over n squared plus 1. This is just n behavior of a rational function. So we just take the ratio of the leading coefficients. We have 1 over 1. This is 1. And we know that 1 is less than 0, it's greater than 0, but it's also less than infinity. And this weird looking horseshoe right here is just another way of saying and, if you're confused on why I drew that. So, since 1 over n diverged and we got a value that satisfies the limit comparison test, we say that the series from 1 to infinity of n over n squared plus 1 also diverges, and this is by the limit comparison test, LCT, limit comparison. Can't you see how much faster this is than the integral test that we did last time? That's why I tend to refrain from using the integral test unless I absolutely have to. Like in that ln n over n squared example, you would have to use the integral test. But with the with the limit comparison test, look at how much less work we had to do. So that's just why I like using comparison better. So we have, now let's go ahead and move on to a little bit trickier of an example here. We have the limit, the series from 1 to infinity of sine squared 1 over n. I'm going to let you guys try this one for a little bit, so feel free to pause the video and see if you can get the right answer. Alright, cool. So, we have the series from 1 to infinity of sine squared 1 over n. I'm going to go ahead and compare this with the series from 1 to infinity of not 1 over n, but 1 over n squared. And you'll see why when we actually take the limit. So we have 1 over n squared. We know that this converges by the p-series test. And so let's go ahead and take our limit here. So we have the limit as n goes to infinity of sine squared 1 over n divided by 1 over n squared. And now what I'm going to do is I'm actually going to go ahead and split up this limit into two limits. So we have the limit as n goes to infinity of sine of 1 over n times sine of 1 over n. And then we divide that by 1 over n times 1 over n. And so what I'm going to do is I'm just going to go ahead and just split this limit into two because that's the property of a limit. We can do that. So we have sine of 1 over n divided by 1 over n times the limit as n goes to infinity of, again, sine 1 over n divided by 1 over n. Now what I'm going to do here is I'm going to solve this limit by a substitution. So we're going to let's say theta, because we're dealing with sine here, let's let theta equal 1 over n. Whenever we do a limit by substitution, we have to change this to be in terms of theta. So we have, as n goes to infinity, theta, or 1 over infinity, is going to approach 0. So as a result, this becomes the limit as theta approaches 0 of sine theta over theta times the limit as theta approaches 0 of sine theta over theta. Now this limit is actually a very famous one. You've probably covered this in your calculus class already, but the limit as theta goes to 0 of sine theta over theta is just 1. And I'm going to explain that just really briefly. So, as you get really close to 0, or for really small angles theta, the sine of theta actually approximates to being that angle theta itself. And that's just going to be visualized through the unit circle. I'm not going to draw it, but you can try drawing it on your own and making theta really, really small. So, since sine theta is pretty much going to equal theta for really small values of theta, this limit is going to be 1, this limit is going to be 1, so we just get 1, we know that's greater than 0, and 1 is less than infinity. So therefore, our conclusion at the very bottom, the series, that is a terrible looking sigma, the series from 1 to infinity of sine squared 1 over n converges by the limit comparison test. And that's it. Those are the comparison tests right there. They're so much more efficient than the integral test, for example, and maybe some other test that we'll do in the future, like a ratio test or the root test. Now, I'll say this though. I don't tend to use the direct comparison because of this. Because you're going to have to make an inequality, and you don't want to do that. just do the limit. The limit comparison, I would 100% recommend that the limit comparison should be used. I would recommend to y'all to use the limit comparison whenever you can. Whenever there's a comparison, use limit comparison. It'll pretty much work. Like, it'll never not work. Unless you choose like the wrong series, it'll work. But yeah, that concludes part 3 of this series, and I hope to see you in future parts.